Today, our speaker is Professor Isabelle Cantat, who is a professor at the University of Rennes in Brittany, France. So just to give you a short biography of our speaker. So she got her PhD in 1999 from the University of Grenoble. And after a postdoc, she obtained a position at Rennes as an assistant professor and then as a professor. She has been a visiting professor at Cornell and Princeton, and more recently she's been awarded an ERC grant in 2017 to support her research on foams and films. So today she's going to talk about the visco-elasticity of foam and films. Please remember that this talk is recorded, so if you don't want to appear and you still have a question, you can use the chat of the Zoom. Otherwise, you just raise your hand as usual. And also, if you're interested in Isabelle Cantat's research, you can have a few papers that are free to access for a certain period of time on the website of the webinar, which is kindly provided by Journal of Fluid Mechanics. All right, so please make a warm welcome for Professor Isabelle Cantat, and the ground is yours.
Okay, so thank you very much for the invitation and for this very kind introduction. And indeed, I will tell you about foam film deformations. I will show you many results and videos and experiments that have been obtained by a young researcher in my group and supervised by Benjamin Dolay, who is now in Grenoble, Arnaud Saint-Gilles, and myself. And most of the results have been obtained by Adrien Buissonnière. So why studying bubbles and foam films? It's because it's part of foams, which are important industrial materials. So you probably know very well as a foam related to food industry, cosmetics and detergents. That's everyday life foams. But they are also very important in the oil industry as drilling mud, for example, or in firefighting. So you see the huge amount of foam you need to, in case of fire beginning. And it is also used for ore separation, but by a technique that is called the flotation. And in many examples, the foam is flowing, and the key word in this talk will be the viscosity. So the viscosity of a foam is measured in a rheometer that is schematized here. And if you measure the stress as a function of the shear rate, you will get something like this data that has been obtained in the group of Arnaud some time ago. At very small shear rate, you see the plastic threshold. And then if you increase the shear rate, the stress increase when you reach something like 1 Hertz. And here the different curves correspond to different liquid fractions. So now in this talk I will be, so the yield stress is relatively well understood in forms, and I will be much more interested in this part of the curve that you can represent after subtraction of the yield stress on this graph to show that the viscous stress is a sublinear power law of the shear rate. So the viscous stress is defined as the stress minus the yield stress. And here you see that the foam is a shear thinning complex fluid. So I won't discuss at all the power law, but I will focus first on the order of magnitude. If I need to select one shear rate, because the viscosity depends on the shear rate, but if you pick this one, for example, we can define the viscosity by simply dividing the viscous stress by the shear rate, and you get something of the order of 1 Pascal second. And the point is that it is much larger than the forming solution in the foam. And the remaining part of the foam is gas with an even smaller viscosity. So it is this enhancement of the viscosity is related to the confinement of the liquid phase in the small films and meniscus in the structure of the foam, but the way the confinement is able to transform the viscosity of the continuous phase into such a large viscosity is not well understood. So this is the motivation for studying at the scale of the film what happens in the liquid phase and how does it flow. So we are zooming on a very small part of the foam, and we see the structure with the films, the meniscus at the boundary between three films, and the gas bubbles in between. So we will play with such kind of system at the centimetric scale and with few films on a solid frame. And the important thing is that we produce free meniscus that mimics the real environment of a meniscus in foam. This meniscus here will be called a free meniscus because it is not touching the solid. And this film, for example, is bounded by meniscus in contact with the solid on this side and a free meniscus on the other side. So now when having produced our system, we will deform the film by simply moving the solid that limits the film and stretch the film. So yeah, already we can ask a very simple question. What is the velocity field in this foam film? And even more simple question, when you stretch the film, are you actually stretching the film you initially had, or are you producing a new film that would be extracted from the meniscus all around that plays a role, that contains a lot of foaming solution and that can play the role of the reservoir? This is exactly the same question as you can ask to yourself, seeing this spider. Is the spider producing a new thread, or is it simply extending the thread that was initially here? So as people are doing fluid mechanics, you will be probably convinced that you cannot build or predict the dissipation of such liquid system if you are not even able to answer this simple question. Are you stretching the film, or are you producing new film? That's very different possible deformation, and we need to do the experiment to answer the question. So here is what you see once you stretch this vertical film. Yeah, so here you see the free meniscus, that's the moving meniscus, and this is what happened in the film. So I remember you, color indicate the thickness, bright color correspond to thickness smaller than 1 micron, and gray colors correspond to thickness larger than 1 micron. So what do we see in this movie? Here you have what I will call the initial film that has been initially produced on your at rest on the frame. And you first stretch it. You know this because you see the color going towards the small thickness colors. And after a while, you begin to see this gray band here that corresponds to a much thicker film that is extracted from the meniscus. And even when the motor stops, this gray band keeps growing, and this relaxes the tension in the initial film. Here you see the size of the film, of the initial film is much smaller than at this stage, and the film relaxes to the color it had a long time ago, and almost the same size and same color. So the answer to my first question is that when you stretch a film, you first extend it, and then you begin to extract new film from the meniscus all around, and it relaxes the initial film. A last remark is that on this last image, all the gray part is at the bottom of the film. It is actually because there is a gravity stratification in the film. This film is thicker, so it is also heavier, and it simply falls down through the film at the bottom of the film. So it doesn't matter where it is. This is a gray part extracted from the meniscus. And you will have to remember one name. This thick film extracted from the meniscus dynamically will be called the Frankel's film by the name of Frankels, who studied this in collaboration with Meisels in the 60s. So this is what happened with the simple experiment of stretching a film. Now let's see what happened when you compress a film. So here, your initial stage is the one you had at the end of the previous transformation, but this time you are in a horizontal film. So here you have two thick films that have been extracted from the menisci, and now you pushed again on your film. So let's see what happened. So this time, this is the moving meniscus. And you see a very nice and regular instability developing along each meniscus with very thin spot of film that invade the thick film. So now it is a fluorescence observation. So this time, white means thick and black means thin film. It's simply fluorescence emission. So my first message is that there is fluid dynamics to do in a foam film. There is plenty of complex behavior, and the velocity field may be very difficult to predict. So now, among all this interesting feature, I choose to tell you in this talk about the film-meniscus interaction. And I will especially address two questions. Can we predict the velocity of extraction of the Frankel's films that you have seen on the first movie? And the answer will be yes. And is it related to the foam viscosity at the sample scale? And the answer will be maybe. And about the instabilities you saw, it was just a teaser, and there will be no instability in the rest of the talk. I will be always in situation where the system is invariant in the direction parallel to the meniscus. So we can assume, okay, the situation will be always assumed invariant in one direction. So in order to address this question, we built what we called a thin film rheometer. So here you see the first version with 5 fins. Here you see one free meniscus. There is another one on the other side. The film structure is represented here. That's a new version with 5 motors, and the deformation of interest will be always the same in the talk. I compress 2 films on the left, I stretch on the 2 films on the right, and I mainly studied what happened in the central film. This central film is horizontal, so there is no problem with the gravity, and it is limited by 2 free meniscus. So it mimics relatively well what could be a free film in a foam, because it is not touching the solid, only a little bit at these 2 ends, but there will be no boundary effects here and there, because everything will be invariant by translation in this direction. So if we want to predict something, we need to measure something first. So we put cameras all around the setup. Here, one camera to measure the plateau, so the meniscus position and size. Another camera here, that is a fluorescence camera. Actually, we put some fluorescein in the foaming solution, so we can record with this camera the thickness field in this central film. And more importantly, we can photo bleach with this laser a small dark spot within the film that will be a perfect passive tracer for our system, because the fluorescent photo bleach or not does not modify the interfacial properties. So this dark spot will simply follow the convection in the film. A third camera is something called an hyperspectral camera, and it is able to record the reflected light along one line, and at each pixel of this line we get the reflected spectrum of white light, and from the reflected spectrum we deduce just by the interference rules the thickness of the film. So we have, with a good resolution, the thickness along one line, either in this film or in another one. So that's a scheme of the setup. And now we can begin to measure things. Let's first discuss measure of the tension. So the problem is actually a 2D problem, as I told you. We can imagine we are in this plane represented here in purple. So the system is something like that. And the position of the meniscus, this meniscus, for example, is entirely determined by these rules that comes from the force balance on one meniscus. So the tension here must balance 2 times the tension here and there, multiplied by the cosine of this angle corresponding to the projection of the force in this direction. So if all the tension are the same, the angle are the big angle here is 120 degrees. But if there is a tension difference between the two fields, this angle must vary. If I stretch this one, the tension will increase and the angle will increase too. And this angle increase will move the meniscus. This should move, but it doesn't. Here you see. So if you increase the angle, you just, by geometrical rule, move this meniscus in this direction. So this is what you see in the middle of the film, seen from the top. That's the initial position of the menisci that you see in white because of the fluorescent emission. And when you stretch this one and compress this side and compress this side, you see the menisci moving a little bit to the right. So to summarize, the meniscus motion provides the angle between the film, and this provides the film tension. So I need to make 2 remarks. First, that the tension is uniform in the film, simply because in the film there is no other forces acting, there is no friction of the air, there is no inertia, these 2 quantities are negligible. So the force balance of a piece of film implies that the tension is uniform along this line. So by symmetry, the tension here is the same as the tension there. So here I characterize these 2 films by only one quantity, which is sigma plus. Same thing on the other side, it's sigma minus. And the last information is that I will show you later that there is no extension or compression of the central film. So the tension remains the equilibrium one here. So from this formula, I put here the equilibrium tension, and I get the sigma plus on this side, and with the same formula on the other side, I get sigma minus. So that's for the force in my system. Now I need kinematic information, and I will first focus on the film extension. And here there is a subtle point, because the extension of the film is not related to the distance between one meniscus and the other. As you have seen in the first movie, there is an extraction of Frankel films from the meniscus, represented here. So the whole film is not a closed material system. So speaking of extension makes no sense. What you want is the extension of some material system. And the initial film that is represented here is a very well-suited material system that you can follow during its deformation. So the aim is to determine the size of the initial film as a function of time with some precision. And to do this, we recorded the thickness along this line, which is plotted here. And we used the volume conservation of this initial film, because you know water is incompressible. And the volume is simply the area below this curve. And that's the initial position of the film, which is of relatively uniform thickness. And then we stretch it, and we recover the same volume in this domain, which means that the boundary of the initial film is exactly at this frontier. And it is actually consistent with this strong increase of the thickness, which corresponds to the extracted Frankel films. So from this tooth distance, I can build the extension of the film, which is actually valid for the whole film, included the Frankel's film, because as the tension, the extension is uniform in the whole film. So now I have these two quantities. I can begin to make rheology by plotting a force as a function of a deformation. So here you see the variation of tension in the stretch film during the deformation. You begin at the point A, which is this situation, and then you stretch, you move the motor, you stretch the film, which reaches the point B, and then the motor stops, but the Frankel film keeps growing. And so when the Frankel film grows, the size of the initial film decreases. And so you will follow this curve in the other direction during the relaxation and come back almost at the initial size the initial film had. And what is very important in this curve is that the two curves are perfectly superimposed. So that's the sign of an elasticity of a non-dissipative process. We can do this for many experiments by varying the amplitude of the motor motion, the velocity of the motor motion, the initial size of the lateral films, and all the data points are on a single curve relating tension to extension. Actually, it's not such a surprising result. It had been predicted by Couder and collaborators 30 years ago, and the theoretical prediction perfectly fits the data. This is this line that relates the tension of a film to the deformations, to the extension of the film, and multiplied by the Gibbs elasticity, big E, which is defined as a coefficient relating the tension of an interface to the concentration of surfactant at this interface. So big gamma is the concentration of surfactant. This is a well-defined thermodynamical quantity that we can measure using this experiment, and the best fit is obtained for typically 5 millinewton per meter. So what is important in this result? First is that this whole result is verified here experimentally for the first time. And this is because measuring epsilon is actually difficult. It needs to be precisely defined, and it's not related to the size of the film, which is a natural object. And the second point is that actually in the community working on foam and foam films, everybody expected this law to be to require a correction proportional to the extension rate. So a term proportional to the interface viscosity. So in order to test this assumption, we built all our experimental data by from the value of the shear rate at the moment of the measure. So here all the point, this line is the average over all the data points having a very small shear rate. And then you get a middle shear rate and the biggest shear rate of the order of 25 Hertz, and every curve are perfectly superimposed. So that's an important result, is that there is no viscous correction needed to the Couder's model. the film have a purely elastic behavior and a non-dissipative behavior. So that's very good. We were happy with these curves, but we still need to understand where does the viscosity comes from, because it does not come from the film. So to address this problem, we have to focus to what happened close to the menisci, and to see again what happened in the central film when you compress one side and stretch the other side. So let's see what happened. Here you see the fluorescence emission and the two free meniscus here and there. So what do we see in this movie? First, let's discuss these small dark spots that you probably saw. This is a photo bleach spot that we produce at this time and that we can follow during the deformation. And this is our passive traces. The second thing you see is this very bright piece of film, which is a Frankel's film, much thicker than the initial film and extracted from this meniscus. So the first remark is that both this quantity is a frontier, correspond to a material point, because there is no mass transfer from the Frankel's films to the initial film. So if this point and this point have the same velocity, it means that there is no extension or compression in this central film. So this validates the assumption I previously made, that the tension here is the equilibrium tension. And so now let's give some physical meaning to this Frankel's film extraction. Actually, it comes from the fact that here we compress the interface and they want to escape this film and to slide over the meniscus in another film. So when the interface slide on the meniscus, it will goes out on the other side, and by going out of the meniscus, it will drag some foaming solution from the meniscus that plays a role of a reservoir. And this is the origin of the Frankel films in the central film. The same thing happened on the other side. Here the interface is pushed in this direction, slides over the meniscus and goes and is extracted on the other side. So actually the velocity of this frontier represents the velocity of the interface going from one side of the meniscus to the other side. And I will call it the transfer velocity. And remember that this velocity is a dynamical quantity and has nothing to do with the motor velocity, which is the imposed velocity, an external velocity. U is my internal velocity selected by the system and governing the transfer of interface from one film to the other. So now we can again try to do rheology and plot a force as a function of, this time, a velocity. If I plot the surface tension difference between this film and this film, so for the extended side, as a function of the Frankel film velocity in the central film, I get something like this. So here again, the time begins here. Here the motor is moving, the tension increases, and the velocity of the transfer velocity is faster and faster. At this point, the motor stops, but the transfer keeps going and at a slower and slower velocity until everything stops at this point. The same thing happened on the compressed side. And so now we have to understand this curve. There is a relationship between the tension difference and the velocity, which is not, but the two curves are not perfectly superimposed. So we have to discuss this and to try to build a relationship that relates these two quantities. And so the remaining part of the talk will be dedicated to the model we can build to understand this curve. So let's begin with what happened close to the meniscus. All the physics will occur in this small square here, and similarly on the other side. But we will take this one as the example. In the film, so this is this region, we are close to the meniscus, but still not too close. And at this point, the two interfaces are moving at the transfer velocity towards the meniscus. The concentration of surfactant at the interface will be denoted big gamma. And then it's a little bit larger than the equilibrium value because we are in the compressed film. And so the aim of the model is to predict the relationship between this velocity and the tension difference between this film and this film. But there is a relationship between the tension and the concentration at the interface. So both quantities are more or less the same because they are related through this Gibbs elasticity that we quantitatively measured using, in the first part of the talk. So I have this concentration and this velocity, and now let's see what happened for both interfaces. This interface flows at the velocity u and can slide freely over the meniscus to reach the central film. But this meniscus, this interface, in contrast, has at the beginning the same velocity, but must stop at this point, which by symmetry is a point of vanishing velocity. So this induces symmetry breaking between the two interfaces that will be at the origin of all the dissipation that we are looking for. And an important quantity is this distance L required for the velocity to vary from its initial value to 0 at the meniscus. So now we need to relate this three quantity to build our dissipative model. And actually all the troubles of this meniscus come from this frustration here. The interface cannot slide to the other side. So our first coupling will come from what we call the Marangoni Law. The parameter will be eta, the bulk viscosity of the forming solution. And the Marangoni law simply expresses the tangential stress balance at the interface. Imagine you have a piece of interface here, and the tension is a little bit larger at this point than at this point. In order to balance the forces, you need a viscous force coming from the bulk in order to be able to write sum of the force is 0 on this piece of interface. And this is true because in the form, no forces are coming from the gas phase. So if you quantify this relationship, you get that the derivative of the tension in this direction is equal to the derivative of the velocity in the normal direction multiplied by the viscosity of the bulk. And actually, because the system is confined in thin film, the derivative of the velocity is something very simple, because the velocity field can only vary linearly from one interface to the other, just because the pressure is 0 in the film. As you can see, the interface here is almost flat. The pressure is 0 by reference in the gas. And because there is no velocity pressure gradient in this direction, because we are in the lubrication regime, the only things you can do is a simple shear. So it seems to be a very simple problem for hydrodynamics. The only solution I can have is a simple shear. So in scaling law, I can build, so I will explain the model using scaling laws for simplicity. So this becomes the tension difference between these 2 points divided by the length of interest I'm looking for, big L. And on the other side, I have the viscosity of the bulk phase multiplied by U, which is also my important parameter, that's the transfer velocity, so the velocity at this point, divided by the film thickness. So I have one coupling for 3 quantities. I need another one. And the other one will come from the diffusion field across the film, from the conservation, so from the mass conservation of the surfactants. So now let's think about the surfactant flux coming here on each interface. The flux on both interfaces at dominant order, the transfer velocity multiplied by the equilibrium concentration of surfactant. And the problem is that on this interface, the flux must be 0 at the other end of this domain. So in steady regime, you cannot accumulate surfactant in this part of the interface. So every surfactant coming here have to cross the film to reach the other interface. And this is described by the diffusion of the surfactant on this small distance, which we can put again in equation. So we need to express the diffusion field, the diffusion flux across the film, which is proportional to the length of the exchange domain, big L, proportional to the diffusion coefficient of the surfactant in the bulk, and proportional to the concentration gradient between this point and this point, so delta C over the film thickness. Now the bulk concentration can be related to the interfacial concentration using this important parameter that I will call the reservoir length, which is a derivative of the interfacial concentration with respect to the bulk concentration. Here again, that's a well-defined physico-chemical property, which is a good thermodynamical property we can a priori measure independently. And so and that measure the solubility of the surfactant. Now I need to transform this concentration into tensions using the Gibbs modulus, and I get my second coupling between U, L, and delta sigma. So from these two coupling, I can solve the problem, which is building a relationship between the tension difference between these 2 points and the transfer velocity of the interface across the meniscus. An important remark is that this model predicts that the tension field should be something like that. At this point, you have the same tension on both interfaces, and because of the Marangoni law that couples the tension derivative to the velocity derivative, when you increase the tension on this side, you need to decrease the tension on the other side. And we can make the remark that the sum of the tension on both interfaces remains constant along the film, which is consistent with the assumption I made previously that the film tension, which means that the sum of the tension on both interfaces remain uniform in the whole film. So now I have a prediction for a relationship between tension difference between the compressed film and the central film and the transfer velocity. I can do exactly the same thing for the stretch film. So now I can compare this prediction to the experiments. So here I show you more data series obtained by varying the amplitude of the motor motion. And we have only the relaxation stage. So the small times, are here. And here you see the velocity decreasing towards 0 and with the time following this direction. This part is the extended side and this part is the compressed side. And let's put the prediction on it. So the prediction we got in scaling laws is pretty simple. It's simply a linear relationship between the tension and the velocity. So we can just put this linear law here. The important point is that we know all these parameters. Big E has been measured by the elasticity of the film. The diffusion coefficient is something we can find in the literature. That's the viscosity of the bulk. Only this one is not very well known, but we have a very good idea of its order of magnitude. So we can test that the slope is reasonable, and actually it is. But it is still not entirely satisfying at this stage. So instead of doing scaling laws, we solve exactly the model I explained you, but with Rheology partial differential equations. And this time we got this black line. We still have the linear part as expected, but we find a saturation only in the stretching regime at high velocity. So where does it come from physically? It comes from the fact that compressing and stretching is not exactly symmetrical, because when you stretch, at some point you deplete entirely your interface, and when you reach a concentration 0, you cannot go beyond. And so when I say that the interface is entirely depleted, it does not mean that I have only water here. Actually, we use a quite complex foaming solution, which is a mixture of sodium dodecyl sulfate and dodecanol. And it would be a long story, but only the dodecanol is important in this story, because this comes very fast to the interface, so is at equilibrium everywhere. So here's the concentration I need to consider is the concentration of dodecanol only, and this one can reach the concentration 0 here, which correspond in the model to a system that you can freely extend without additional resistance, because only if you have no more dodecanol at the interface, there is no more elasticity in the field. So here it's a little bit better, especially because this saturation is predicted without any adjustable parameter, because it depends only on E that we know well for this precise foaming solution, because it has been measured and deduced from the elasticity of the film. So this is a good validation of the model. This has the right slope, but we still have plenty of points not on the curve. So we need to improve a little bit the model. And we believe that the assumption that need to be modified is that the flux is 0 at the meniscus. Actually, we solved the problem in the lubrication approximation, that it's only valid in the flat film, and we cannot reach exactly the point where we know for sure that the velocity should be 0. So the scenario is that when you get closer to the meniscus, when entering the meniscus interface, the surfactant can go into the meniscus that will play the role of a reservoir. So at this stage, we choose a phenomenological law to describe the boundary condition at this point and to say, okay, all the flux coming here should go across the film or be absorbed by the meniscus, depending on the concentration here. If the concentration is very far from the equilibrium one, you will dissolve a lot of surfactant. So playing with this parameter, we can build this kind of dashed lines, which distance from the previous model is a function of this adjustable parameter here. And doing this, we can find a limit for all the data. So the data are in between both models. So what is a possible scenario for this story? Is that, remember, the time is small at this point and increase when you follow this line. So at the beginning, the meniscus is at equilibrium and can easily play the role of a reservoir. So we are close to the dashed line model. And during the deformation, the meniscus get depleted on the stretch side or saturated at the compressed side and cannot absorb any more surfactant. So at the end, we reach the model where the surfactant plays no role anymore. So this will have to be confirmed by changing the forming solution and investigating a little bit more what happened, what are the exchange, not between films, but between the interface and the meniscus. But we can imagine that a diffusive law would be found in the meniscus relating the source of surfactant here to the diffusion field in the meniscus. The problem here is that we are at a scale a little bit too large for the convection to be negligible, so we don't believe that diffusion is a dominant behavior here. That's why we kept it as an adjustable parameter. So now what did we get? Can we, with these two relationship relating tension and film extension and tension difference to velocity transfer, can we predict the global behavior of our 5-film system? So the schematical representation is this one. We have a spring on each film and a viscous dashpot on each meniscus. And putting these two information together, plus the kinematical conditions that say that the spring here can relax or can be deformed, either because there is some transfer from the other film, or because this is U here, or because the motor moves. This is a dB over dt. B will be the size of my film here. Then we can build a kind of Maxwell fluid model that predicts the curve we get, for example, for the tension as a function of time when we stretch the film. Here I stretch my film, the motor stops, the film relaxes with a certain time scale. Same thing in compression. And these time scales are either governed by this law if the meniscus play no roles, or by this law when I have some exchange with the meniscus. If the exchange with the meniscus are diffusive, I can predict this diffusion time here and say that the characteristic time of my Maxwell system here scale like the square root of t corresponding to the classical diffusion rules with square root of t variations. So that's for my 5-film assembly, but obviously a 5-film assembly is not as the most exciting system in the world. What I would like to do is something relevant for a foam sample. So can we upscale this result at the scale of the foam? To answer this question, we first need to come back very shortly about to this length scale, big L. From the two coupling I explained to you, I can deduce the scaling for this distance L, this which scales like this, always as a similar combination of all my physico-chemical parameters. And for our experiment, the typical the scale we predict is 100 micrometer. And actually that's crucial, but because it is a typical bubble scale in a foam. So if my bubbles are much larger than 100 micron, there is no reason for the system to behave in a different way than the one I explained to you. If in contrast, the bubbles are smaller than 100 micron, then the sheared domain invades the whole film, and there is no more as a central part of the film where the two interfaces behave the same way. So what we predict is that for bubbles smaller than L, the shear domain invades the whole film, and you get such kind of pattern. And for bubbles larger than this length scale, then you get mainly a stretching and compression of the film and dissipation only close to the meniscus in a small domain scaling this way. So now we cannot deduce anything for what happened in the foam if the bubble are smaller than L, but here you see it scale like the film thickness, and we also believe that the film thickness should be smaller in a real foam because capillary section is higher. So let's assume we are in this case in the form, and let's see what we can deduce from our scalings. So now we tried with an oscillatory experiment, and we haven't tried to figure out what should be exactly the velocity field in the form, but we just trust that the scaling law we add for the dissipation at the meniscus should remain valid for a slightly different geometry. And we estimated what should be the loss modulus on the basis of the scenario we propose. So it's simply the frequency times the elasticity of our system multiplied by the internal time scale of the system. This is, and actually the elasticity of our Maxwell fluid is the Gibbs modulus divided by the bubble size. If we assume that, and we take the further, and we assume that we are dominated by the exchange with the meniscus with a diffusive time scale in the meniscus. So that's a lot of assumptions that we are not able to test at this stage, but just, okay, to play with the idea, we combine these two information and got a prediction for the JSGON double prime. And actually, it is certainly not a proof that we are relevant for form, but it's a big encouragement to keep trying to understand what happened in the form with the tools that we developed, because we get exactly the scaling that we would like to see, which is a square root of the frequency for something that decreases as 1 over the bubble size, and with a prefactor of the right order of magnitude when we put the number we got from our experiment in this prefactor. So this is a story that should continue in the future, but we hope that this work could be relevant for form. So now the take-home message to conclude is that form films are elastic with no role of the interfacial viscosity. Second, there is a generic frustration at the meniscus, simply because if one interface slides over the meniscus this way and its neighbor this way in order to avoid any shear at this point, then you don't know what to do with the third interface. It cannot satisfy both arrows, red and blue. So actually the story would have been entirely different if the meniscus had 4 neighbors, but a meniscus connects 3 films, which is an odd number, so it generates a frustration. We predict that the main dissipation occurs in a small domain between the film and the meniscus of extension big L that can be predicted as a function of the diffusion of the surfactant, the Gibbs elasticity of the interface, the viscosity of the bulk, and the solubility of the surfactant. And the last prediction is that large bubble should be mainly stretched, and the film in the large bubble form should be mainly stretched and compressed, and the film in a small bubble form should be mainly sheared. And so that's my conclusion. I thank you for your attention, and I thank again all my collaborators who performed the theory and experiments. Thank you very much.
So we start with one. So I'm no expert in foams, unfortunately, but I was wondering whether like how this model would be, I don't know, modified, or does it still work when you have a reconnection of vertices when you shear the foam or something like that?
You mean one film size goes to 0 and
yeah,
there's a T1 scenario, etc.?
Yeah.
Yeah, that's a good question, because there's transformation, key transformation in forms. I would say that everything that happened before the contact between the 2 menisci can be relatively static, or at least it goes at the rate imposed by external constraints. But what is probably more important for the dissipation in form is what happened just after the reconnection, because at this stage, the structure is unstable and you have a very fast stretching of the newly formed film. And in that case, at the beginning, so you have a big vertices that is cut in two pieces, and there is a new film appearing between the two meniscus. And at the beginning, the film is so small that you cannot really stretch it. You need to first produce some film. So at the beginning, you are almost sure you will extract some frontal films from the meniscus. But after a while, I think you should have the same competition between stretching and extraction as soon as the size of the film is large enough.
You seem to neglect in your flux balance absorption and desorption rate of surfactants. Is that reasonable?
Yeah, so at this stage, we use the simplest possible model. So we assume that we are limited by diffusion only. Probably it depends a lot on the surfactant. I would say that even if the diffusion is very fast because the film is thin, I had the idea that it was a reasonable assumption, but actually it's the prediction can be easily transformed to take into account something that would be limited by adsorption and desorption rate at the interface. The point is that you need to determine the time scale the surfactant needs to go from one interface to the other, whatever the mechanism. So the answer is I don't know. But if you think I should take it into account, I will.
How would this work with particles absorbed at the interface? Could the frustration explain the high stability of these particle stabilized foams?
So yeah, again, I don't know. The frustration is something that is a priori very generic because, okay, you can just see at this pattern, it's very clear. It's pretty easy for a single interface to go from one film to the other because the meniscus is the zone where the friction is reduced in comparison with the film because the confinement is not so important. But you cannot be happy on the three interfaces together. So this imposes that when you try to deform a form, you will either shear the film or compress the interface. And because shearing the film is the most dissipative feature in the structure, it will resist a lot. And so I think this frustration generates strong compression or dilatation of interface, whatever is on the interface. It can be surfactant or particle. I think part of the story should be robust. But so this is my answer. I cannot answer if it is at the origin of any kind of stability, because as everybody knows, nobody knows what controls the bubble stability. That's an even much more difficult question.
Thanks a lot for the very nice talk. Just, it might be a stupid question, but you didn't talk about the curvature around the meniscus. Is it just negligible?
You mean the curvature along this line?
Yep.
Yeah, so it's not negligible at all in the story because it controls the Laplace pressure here. But actually for the tangential motion we are dealing with, it's not important. And what actually the model we wrote is only valid in the thin film part, and the meniscus plays a role of a boundary condition. But we carefully checked that the dissipation was certainly negligible on this part of the way. So the interface should get closer to the meniscus and then slide over the meniscus and reach the other side. And this part of the way is almost free in the dissipation, if we are dealing with dissipation. There is no big dissipation associated to this part of the path. So to answer more precisely the question, there is no need to neglect or take into account the pressure here, because everything happened a little bit outside the meniscus, and when you reach the meniscus, you can flow easily. So the Laplace pressure is there, is important, but does not influence the motion we are dealing with, which is a tangential question, whereas the curvature is more important for the normal forces.
Okay, thank you. Thank you very much.
Have you considered an axially symmetric geometry instead of translation symmetry?
We made a collaboration with Anne Lorbiance, who asked the previous question, taking into account this axially symmetric, some axially symmetric bubbles. We haven't done it in the frame of what I present to you today, but I think many things would be similar. Of course, if you have a radial motion, this motion induces extension just by geometrical effect, but probably it could be taken into account. So actually, many previous experiments in this domain were done in an axisymmetric geometry, and it was much easier to develop this experiment where we are invariant in one direction. So I would say experimentally, yes, but for the model I presented you, we just tried in the geometry I presented.